We can hold it or you can have the living noise. Oh, something like this.
All right, set aside the worksheets for now. Go ahead and get out your 6-3 notes. Okay. We are going to put in a little bit of legwork on the front end. The main idea that I am trying to capture here is very, very simply that we have done 6-3 already. We are just now going to be looking at a specific case where the mean is going to be something slightly different than just like the number that we're given, and where the standard deviation is something that we're not given, but something that we can calculate very quickly. Right? Otherwise, exact same thing. So just as kind of like a reminder of where we were. So when we're talking about our confidence intervals. The basic up there on the board already kind of definition that SDC is going to give you guys is just very simply our mean minus the error up to our mean plus the error. This is just like the gist at its most basic level, what a confidence interval is. Do you have a question? Okay. Yep, you're good. Now we can go a little bit further here. We know what EBM is. EBM, the error, has changed slightly depending on the scenarios. We had some definitions where like we knew what sigma was. What happens if I know what the population mean is? What standardized test score do I use, or what standardized score do I use? And then what should I use for my standard deviation? So if I know population sigma, if we know sigma,
Yeah, we know sigma.
then we need to use
over.
So if sigma is known, independent of how big our sample size is. So in this case, it doesn't matter if n is 5, it doesn't matter if n is 100. We can go ahead and use our z-score times sigma over the square root of n, just because we're saying we know what sigma is. Right? We don't have to guess. We don't have to make an approximation. Sigma is known. And so we'll go ahead and use the z-score paired with this. So this was like if sigma is known. But if sigma is not known, then we are going to have to do what Wesley here suggested, which is we don't know what the standard deviation is. Again, we have two different options. What happens if we are taking from a small sample size? Am I allowed to use a z-score if my n is like 15? No, if I don't know sigma and my n is small, what's our cutoff for small? 30, so anything below 30. If my n is small, then I'm going to use my t-score rather than my z-score times, we don't know sigma, so we'll use s instead, divided by the square root of n. This is what we were looking at yesterday. So this is if sigma is unknown and n is below 30. All right, and then the one that we didn't really, I didn't put this to a formula, but I've said frequently this idea that if n is big, then we can kind of go back to using z-scores. At the point that we hit 30, the difference between the t-score and the z-score is really, really small. So we just kind of switch back to using z. Not that using t-scores would necessarily be wrong. It's just not really all that different than if we were using the z-score. So if n is big enough, then we can say, well, we can go back to using the z-score. We still don't know what sigma is, so we'll still use s. But because n is large enough, it doesn't really matter. But essentially, we had this idea of we're taking our standardized test score, this z-score, this t-score, whatever, multiplying it by the standard deviation for a sample. Why is this the standard deviation for a sample? What makes it a sampling standard deviation? The sigma is just the original population standard deviation. But how have we transformed it into a sampling standard deviation? What have we done to sigma or s? Divided it by the square root of n. This act of dividing by the square root of n is what is transforming it into this sampling standard deviation. Now, my claim here, what I am trying to kind of get across here is this idea that everything that we are doing in 6.3 is just this, except we can be a little bit more specific about what our standard deviation is, and our mean is going to look a little bit different. Not that much different even. It's basically going to be the same thing. So let's address the situation, the specific situation that we are going to be dealing with. We are going to be looking at essentially binomial experiments. Digging deep from Unit 5. What did it mean for my distribution to be a binomial distribution? What was essentially the big condition that we had to fulfill? So we had two something with two. Not two numbers. What made something a binomial? Not two values. Values isn't my favorite word there. Two something. Numbers is definitely not my favorite word there. Heads or tails. Two possibilities, two outcomes, things of that nature, right? So either, not sample size being two, but either success or failure. Right? Either we can succeed or we can fail an individual experiment, and then the sampling is taking a bunch of experiments all at once. So we had specific values for what we could say for, let's talk about the mu that we can get. Let's talk about the variance, and let's talk about the standard deviation here. If I'm working with a binomial, how did I calculate the mean for what we have here? The mean of a binomial. Nope, even easier. Nope. Nope. Nope, don't even need z-scores. If I have a weighted coin that wins 70% of the time, and I flip 10 coins, how many successes do I expect to have? 7. How'd you do that? So what'd you do with those two numbers, the 70% and the number of trials? You multiplied them together. Okay, let's refocus this a little bit. There's a lot of noise going on. All right. N times P is our mean. What does P represent? Of success. Okay. How did I get variance? We had this really long way of like the e of x squared minus the e of x all squared, and that was fine, but we had a much easier way to do this. What is variance for our binomial? NP, yeah? Sure, yeah, we can absolutely do that. You'll also see this as n times p times q, where what does q represent? That is the probability of failure. And how do we calculate probability of failure if we know probability of success? 1 minus p. No, 1 minus p because 1 is bigger and we want the positive value. Okay, final one. How do I go from variance to standard deviation? Square root. Okay. What 6.3 is going to do is it's going to say, well, rather than focusing on the expected value, the expected number that we are seeing, let's just isolate that probability. Let's talk only about the proportion. So this would be like if I were to go around this room, sample all 20 of you, and get that 8 of the 20 are wearing earrings. Then I want to use the 40% rather than saying that 8 people are wearing earrings. So I would rather say 40% of people are wearing earrings rather than that 8 people are wearing earrings. It's the same idea. It's the exact same notion. Essentially, what we want to do is we want to get rid of this n here so that we're just focusing on the proportion, so that we're just focusing on the percentage. When we do that, we'll say here, we're going to focus just on the proportion. Our mu all of a sudden is just going to be that p, that probability of success. If I succeed 57% of the time, how often do I expect myself to succeed? 57% of the time, sure. My variance is now going to be just p times q. Again, I'm not caring about what's going on with n. And my standard deviation will, again, still just be the square root of p times q. Okay, so this is fine. This is great, perfectly adequate. The only issue is we're not going to be getting these numbers as population values, right? Mu being equal to p implies that the true value of mu is equal to p. Sigma being equal to the square root of p times q, the true value of sigma. Instead, we're getting these from samples. So we're not going to be able to use mu. We're not going to be able to use sigma. What do we use instead of mu when we want to talk about the mean of a sample? X bar. So X bar will be equal to, now P, just like mu, is technically a parameter. So we don't know what P actually is. We want to guess what P is. How have we communicated that in the past, that I'm making a guess as to what this value is going to be? You're not that far off, actually. It's going to be P hat. I was like, Y hat, we're guessing as to what Y is. P hat, we're guessing as to what P is. And then instead of sigma, what should I use? S for standard deviation. And this is going to be the square root of, well, again, we're guessing what P is, and we're also guessing what Q is. And the only thing that 6.3 adds is exactly this. It's the idea that this X bar and this X bar are the same thing, and that this S and these S's are the same thing. That's it. All right. So as far as the relevant notation, we said that P is ultimately like what we're trying to estimate. This is like the true or the population proportion. You can also have this presented as like a percentage. Either way is fine. P is technically the proportion, but we could talk about like 0.57 as representing 57%. Just know if I ask for the proportion, it's not the percentage. If I ask for the percentage, it's the percentage. Sure. P hat, we said is our sample proportion. Or percentage. And then Q hat is like, it's the sample of like not being a part of the proportion. So I'm going to call it the sample not. Linguistically, it's a little bit awkward. But just the idea, it's P and Q, right? P is the likelihood of success. The likelihood of success is 70%. What's the likelihood of failure? 30%. All right. Same idea. So our confidence interval, exactly the same thing. It is still X bar minus the error, X bar plus the error. That has not changed. That will literally never change. That is always our confidence interval. The error has also not changed. I'll go ahead and tell you with the examples that we're going to work with, N is really, really large, like hundreds or thousands large. So we never really have to worry about the t-score, z-score issue. It's pretty much always just going to be z-scores. Not that we couldn't do this with a t-score. Totally, totally could. The ones we work with will be z-scores. Times, in this case, our S divided by the square root of N. Exact same thing. Except here we're saying, okay, I have a little bit of specific knowledge. I know that X bar is actually going to be some kind of percentage, some kind of proportion. And I know that S is going to be the square root of P times Q. Okay, so if we wanted to, we could jam all of this together. Sure. And make it look really, really scary. Oh, sorry, it's not even X bar anymore. This is now P hat. But again, it just looks scary. It's not actually all that scary. S is still S, but now we can calculate it. And X bar is still X bar. Now we can calculate it. Z of alpha over 2 is Z of alpha over 2. That's even easier than t-scores. Square root of N, always dividing by it. Not too tricky. All right. Questions with our definitions here? Or would it be helpful to kind of see an example in action first? Sure. Let's look at an example, and then we'll see if we have any questions. Okay. First example, this is just a quick reminder on how to calculate proportions. It's here, so we'll review it. So looking at the proportion or percentage or what have you of people who have air conditioning given the sample, how do I find the proportion of people who have air conditioning? Or the percentage of people? 108. Is it just 108? Yeah. Divided by, what's our N? 160. Yeah, just 108 divided by 160. Tells us that about 67.5% or 0.675 out of the one people own our air conditioning. Okay, how do I go from P to Q? 1 minus P, which is 1 minus 0.675, which is about 32.5%. Wow. Hopefully fairly rudimentary, not too horrible yet. Give it time. We'll get there. We won't. This is trivial. All right, let's take a look at our first real example. This will be more in line with kind of what we're working. So we're told a sample of 500 nursing applications included 75 for men. We are trying to construct a 90% confidence interval to see what the true proportion of men who apply to the nursing program should be. First of all, is our value of n large enough to use z-scores, or do I have to use t-scores? I'm going to use z-scores because it's over 30. 500 is a lot more than 30. So n here, which is our 500, want to note here, can use our z-scores because n is greater than or equal to 30. Sure. Could we use t-scores as well? Absolutely. They're just going to give us about the same answer. Okay, what is the z-score that is associated with a 90% confidence interval? Does anyone know that off the top of their heads? The z-score associated with a 90% confidence interval.
1.6.
1.64. How would we calculate that if we didn't know that off the top of our heads? Inverse norm. And then center. I think it's like 1.644, something like that. Yeah. Interestingly enough, the t-score is like 1.647. So it is a little bit off. It's not like perfectly aligned, but it's like basically the same thing. Or 0.003 off, which is pretty close. All right, so now we just need to figure out what our x bar and our, not sigma, because we don't know sigma, but our s, what these are. So how do I find x bar? Well, what is x bar the same as for these kinds of questions? That's just the same thing as p hat. Okay, so what is p hat here going to look like? $500. Very good. It's about 0.15, about 15%. Okay. And then how do I find my standard deviation? What does that look like? So that's going to be square root of p times q. And then how do I find q? 1 minus the value of p. Yeah, perfect. Which is equal to the square root of 0.15, awful 5 times 0.85. Something like that. Plug into your calculator, see what it is. I'm actually just going to plug that directly into our test. I'm not asking you to do this here, but if I were, certainly could imagine, say, hypothetically, like, I don't know, in a test that we had on Wednesday, me asking what the margin of error is. How would I calculate the margin of error here? So that'll be the actual confidence interval piece to it. But I'm just looking for the plus or minus bit. What is the margin of error for what we have here? To
Is it?
S?
Yes, is that like?
Yeah, 0.3 something. Yeah.
I'm gonna make sure.
I didn't plug it into my calculator because I'm going to plug that directly into my test, but yes.
Oh, you have to do, Z-score.
Yep, z-score times. If we knew that, yes, but if we don't, then we use S over the square root of n. Okay, what is the z-score that we found? 1.64. What is our value of S? Well, that's what we just calculated here. So that's like the square root of 0.15 times 0.85 divided by, and we said the square root of n would be 500. Plug it into your calculator, whatever that is. Here, well, I'll take a look at that. So this would be 1.64, 1.64 times, so the square root of 0.15 times 0.85 divided by the square root of, make sure when you do the division, you're on the outside of the square root here, just to make your life easier by getting the correct answer. Apparently the margin of error is about 2.6%, so 0.026. Okay. And then certainly we could do like subtracting that from the mean and adding it to the mean. If I wanted to do this in my calculator, where would I go? For our Z interval? Stat, tests, 7. We get an add. For towels, very good. Awesome. This is actually already what it is. If you plug in that value, this is already there. What is our value of n? We said 500, and we wanted 90% confidence. And so hitting calculate, I get that we are between 0.124 and 0.176. 176. Quick reminder, what does it mean that our 90% confidence interval looks like this? So we are 90% sure. In this case, we're not looking for mu. What are we looking for? P, which is basically mu. It's like the same thing as mu. So we're 90% sure that P falls between these values. Yes, Nathan. So if you go to stat, slide over to tests, and down to the Z interval test, then that'll, and the mu that we use is the 0.15, the S is the square root of whatever, and then you're good to go. How are we feeling? Hopefully, like the exact same thing that we did in 6-1, except we have to calculate what S is rather than just being given what S is. It looks like a lot. This is ultimately the answer that we're looking for, which we did with our calculator. All we really needed to do was figure out what S was and figure out what X bar is. I wanted to show you the EBM calculation, the error calculation, because I could reasonably ask you to do that, but it is not what this question is asking you to do. All right, take a stab at the second example here. We do not. I mean, you could you score that each time, but it's 1,000 is bigger. Oh, inverse dollar. What's the Z score that we always use for 95%? You just get 1.64 is 90%. 1.96. I think 1.92 is 90%, if I'm remembering correctly, but I'm not. But you can also do inverse.
What is this?
It's giving you 120.
Yep.
That's right.
Area is, it's a big area.
Cultures, arts.
Area is.
How do you do that?
Yeah, it's 120. So now I know.
1,000, where do you get 1,000?
Which technically you didn't need.
It's just-
but your calculator will do this.
That's one of the 0.9
See what the relevancy score.
But it's.
But you have to do it.
Second.
That's what I work.
That's what I did, but
Yeah, you need to find.
and and also is it
Or you need to find X bar.
it's 0.1.
That
And is 100. It's on 1,000, my bad.
So this is like.
I just, it's the 0, what the hell? And it's. Q. Oh, the Q is this number.
That's what I actually discussed.
This is P, this is Q. So you have to divide it. You have to times it by.
So the Our calculator, I think it says we can use.
Yeah, X bar is X bar.
Not that.
S is in. Sorry, no, S is just the circle with the line.
Yeah, and so you just need your mean and your S.
So.
Whatever you got. Oh,
Well, we already know.
and
Do we have to figure out the air? Do we still need to figure out the errors?
No, you don't need to. I mean, be sure that you are able to.
Oh, yeah.
Like, but this question is not.
So we didn't need to do the.
You said GUI.
But it's good that you're able to, because I will certainly, that is certainly something I could ask. Don't forget that it's the
Chief of the,
That's why you're.
of the. Is it donut dish?
Otherwise. it's-
So.
Scott,
or-
do we have any data? Yeah. Well, you need to find the same thing. X bar is the same thing as, Oh. Yeah. That X bar is the thing else. Yeah. What's your? I can't tell you what. Well,
This one, is this one was 6 years?
Probably. No, but like. I don't care about this thing. I don't care about what it's.
And more such, right? No, I can remember. I think it's a baby bag. Wait, it's all 6.3.
Yeah. I mean, we'll have to calculate and, but like, that's the exact same thing. Six water. So, okay. Is it, you should get about the same.
And what's the answer to this? Do we have to find that?
Yeah, that was great. It looks like you're almost there. It looks like you're.
The story.
Okay, let me see your. You might have used. 25. You actually might have.
We have 5 more minutes, guys. I think so. Because I just put.
You did, yeah. Did you do the dividing by the 1,000? Oh. One minus.
Yeah.
Okay, so when you.
Of course, one punch together.
Yeah. One minus that's what you do. So when you do this, when it's just asking for like sigma or s, you're just gonna put the numerator that you're gonna put the divider.
It'll do that. And there I just tried to put that.
Oh, you should put the 0.824.
Well, it's like always be there.
That would be
It's this number.
Then next to-
Divided by it. That must be fine, the probability.
So that's what else. Yeah, like that.
Perfect.
Definitely better review.
Got too much.
See that?
Yes.
Why didn't you get it? 0.8004. 0.84. Definitely.
Actually, that's tough to bring it back.
So. It's definitely better.
Yeah, he's a move, right?
It can't be the
One.
It's just not down.
Somebody can.
Yeah.
Nothing about it.
This is your. Stack those. Actually,
You should have a sad that.
Oh,
And then stop in all those numbers and then you know how to give you like. Just to give my.
perfect.
Oh, it's a great.
Excellent job. Very, very nice.
Me too.
Alright.
It's definitely. Got it moving down.
It's not hard.
I mean.
Oh, you can be smart.
It takes us a going for some rod and.
This is our stat again.
And which one is it?
One. I did not take numbers. You know, just one.
So we go to.
We go to.
So ultimately, what we want to do is. All you need to do is.
So
What information you need for hours and we know and
Just.
Yeah. I'm missing sigma, but ultimately. Okay, so what is p hat? How do we?
Oh.
They're like, they're both.
I'm not sure how to calculate.
Well, that's,
I'm the same brain.
that's so most, yes.
One fact.
I wouldn't.
Oh, did it automatically
Yeah, we have to change the percentage.
Wait.
Yeah, don't, I wouldn't say that's a
That was very nice. Pretty far game.
And then that would be excellent. We'll see.
So Scott, me, you and Brock. Me, you and Brock staying on business.
That's our.
Stop it.
And then S was that square root, p times. Let's take a look here. I just want to focus on identifying the relevant information. So this would be N, X bar, S. While we're here, let's go ahead and say what Z value would be relevant if I were asking for the critical Z value here. 1.96, inverse norm, 95, blah, 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 famous. What is our value of N? 1,000. What is our X bar? All right, same thing as P hat. And then how do I calculate S? Times Q, so 0.824 times 176. Just like 0.381, blah, blah, blah. Sure. All right. And so we are going into our Z interval. We wanted this to be 95%. We said we had 1,000 for N. We said this was 0.824. And then we said that this was, I'm just going to use the exact value. So the square root of 0.824 times 0.176. Enter. All right, apparently we are between 0.800 and 0.848. That's for S. Taking the square root of that. And that's the interval. Yep. No, it was 2. It was 2 here. Three is reasonable. I'll tell you if it needs to be anything else.
It's like opening interval and then n-1.
So the area, so Dylan, the area that you're looking at for the T of alpha over 2? Is that what you're, is it the front page of the worksheet? Yeah, finding the T value. So you're going to second vars. You want inverse T. So right under inverse norm is inverse T. Your area. So if I'm looking at a 95% confidence interval, we take the leftover area, we split it in half. So if I have 0.95, I'm taking my 0.05, cutting it in half to 0.025. That's the area that I'll use. Degrees of freedom, 18 minus 1, 17. Yeah, so always 1 minus, or whatever it is, minus 1, your sample size minus 1.
Yeah, I would like splitting up one.
This is great. If you feel good about this, then perfect. You can do this. It'll work. It's awesome. I wanted to introduce this to you because I feel like a lot of people really struggled with the inverse norm versus normal CDF. And now we're going to be juggling like 6 different calculator functions. So I wanted to show you how to do this with the old technology, with what we had before showing you a new calculator function to do the exact same thing that we're doing. All right. So one entirely viable, not even particularly burdensome way to do this is to just figure out what the proportion is, to figure out what S is. A little bit trickier. That's a formula that you have to know. But it'll be given to you on the sheet, I'm pretty sure. So figure out what the proportion is, figure out what S is, plug into the calculator. Not too bad. Not too bad. The other way, which again, totally fine to do this, we're going back to our tests. And we are going to scroll down until we find a 1 proportion Z interval, which is what we're looking at here. We have a single proportion, we're constructing a Z interval. Let's use this one. The X that we are going to use is the number of successes. So in this case, how many successes did we have? The number of successes. Yeah, just put the number. It'll do that calculation for you, which is super cool. 824. N is 1,000. And what is our confidence level? 95. Yeah, does it for you. But all that work is just calculating this, right? It's just the square root of it. It's not.
I ain't gotta do any of that work anymore.
I got
Grounding don't fall.
I'm locked in for this test. This test is about to be my thing. About 67.6. Hey, this next quiz is gonna be easy. You're gonna see some 100 popping up. How's really good? How's really good? Every dollar. Thank you. We get it.
Any questions with our
Because I got it.
questions and comments?
And then 6.6. Don't worry about the 6.66.
That would have been great.
Yeah, you lucky.
Even if you take it.
So I just dropped the low. So.
Got about 15 minutes left. I want the 6-2 worksheet that you guys had turned in by the end of class. About 15 minutes. And if you are finished with this, then I don't have 6-3 uploaded yet, but you can work on the 6-2 class. And if you're done with both of those, then you can take a stab at the hypothesis testing stuff again, which again will be the bonus on the test that we have in like, I don't know.
This is big.
No.
Go ahead and give me some. I think.
We all know. You don't have the
They just in the back.
Let's do it.
This stuff that I said. Yeah, they look at the difference.
Okay, but you said that before in like 0.1.
Yeah, you can ask.
But it's something with that too.
What you mean, pretty bad, but.
I think it's just that it might be different. We didn't. But they.
Yeah, but he's nowhere near. Like, on number 8, he's 9. The hypothesis 7 is not. And then on the last one, you do the 3.801 and 30. Take it wrong.
Yeah.
That's what we're gonna do.
Okay, so when you're folding glass on your body. What's you on the last time?
That's that, whatever.
Dude, I'm doing my homework.
So.
It's right. It's not that's something that we. I didn't go to that. Unless you need, words, no. You guys just. No, spaces. I'll go.
It'll do the adjustment.
It's the one that needs it.
It'll find degrees of freedom from like that.
So you get it.
48. Thinking about 100.
Did you see which one was it right between? And him.
But only one of them gives.
I put these into the theater.
They're having a competition.
It's not.
Clearly someone thinks he's right.
So I think this number
It's close.
Oh.
Wait, but it's only slightly, it's not just completely only rounded. Did you solve it by like hand?
It might be, you might be doing the dividing by three square root of 8 thing, so you just wanna enter 7.5.
Okay.
Or did you?
I
Oh, you did it right here. Okay. Then let me, it might be.
No, it's wrong.
Score.
All you want.
Inversely, we have an area 0.025. Okay, when you did the inverse, I think you did 0.05, and you forgot to split it in half. Yeah, you forgot to split the area in half. So the score would be like 2.36. Yeah, but otherwise it's good.
No.
Otherwise, all right. Very close.
What did I tell you?
Oh.
I'm just testing on. But that's a name.
So once you have this.
I've never seen a boy so excited. Excited enough to spend down.
Got the wrong tell you. I do. And fill in.
I can still like take this action.
Glad.
Yeah, everyone knows me. What are you doing?
Is the hypotenuse thing to add the extra credit?
The hypothesis testing?
Yeah.
Yes, that is extra credit on the test.
There's actually.
That'll be like the plus 5 points. It's also very much on the SDC test, which is part of why I really wanted to cover it, is because like it will 100% be like a major part of the test.
Extra credit.
Yeah, there's